using a Bonferroni correction, we found this. If you can use the word Bonferroni, then life is good. In reality, the most smaller sample sizes can't pass a Bonferroni correction. In which case you have to deal with that. My solution is, and most statisticians would say, well, you use least significant difference. Least significant difference we can mathematically prove is appropriate as long as, get back over here, as long as you get a small p-value here, then least significant difference for multiple comparisons is justified. Which is a wonderful thing. So that sometimes we get crap for multiple comparisons as statisticians, but we know how to respond, and we know how to argue with reviewers that come back and say, oh, you should have done a Bonferroni correction. Well, it turns out we know how to prove that as long as we get a small p-value here, then least significant difference is okay. So I have an example that this is a paper that I was helping with coming out of Root and Riddle, the equine hospital. And the reviewer said that the sample size was too small for odds ratios to make sense. And that comment makes no sense. We made a confidence, so if I reported that the odds ratio, or we could just say I reported that the mean was 17, and then but the sample size was 5, then the reviewer would have a point because I only reported the mean. But we actually reported confidence intervals in the paper because that's what responsible people do. Oh, there you go. Responsible applied statisticians report confidence intervals. You do all the p-values you want. You can do whatever the heck you want, but you should have confidence intervals because that tells people where you think the parameter is. So if I report the mean is equal to 17 without a confidence interval, then the reviewer can rightfully complain. But if I report the confidence interval is between 13 and 21, that depends on the sample size, right? A smaller sample size, bigger confidence interval. Bigger sample size, smaller confidence interval. You have a better idea of where the mean is. So this is why not always, but almost all, whenever possible, you should report confidence intervals. And so the reviewer in our odds ratio case has no complaint because we put a confidence interval on there, which depends on the sample size, and therefore we're taking the sample size into account. I have to write that sentence so as not to insult the reviewer. The reviewer happens to be the associate editor who thinks he or she knows what they're talking about, but really they don't. So, but I could still say that reasonably nicely. Because I could just say, well, you're full of crap, which is what we say, by the way. Statisticians are not nice people. If there's a room full of statisticians and we're talking about this kind of stuff, we call each other out all the time, and you know, we still go drink beer afterwards, so it's okay. But if you ever see two statisticians go at it, just because they're not being nice to each other doesn't mean that they're not friends. Just means they're having a healthy discussion about what the appropriate p-value is, or method, or they do the artificial intelligence people and the statisticians get together? Not very often. It's getting more common though. It's starting to get along a little better as we understand each other. Okay. Example. Egyptian skulls. I have no idea where this, oh wait, we have a reference. Multivariate statistical methods. Oh, it's from the small data set book. There's a cool book called Small Data Sets that we used to use all the time when we were looking for examples of our statistical theory, because it's full of small data sets that we could use as examples. The trouble is that now we always have data sets already, or typically have data sets already before we're doing methodology. So I haven't opened the small data set book in a while. But it's an example of multivariate data. So what do we have? 4 measurements were made from male Egyptian skulls from 5 different time periods. How do they know they were male skulls? I don't know. Ranging from 400 BC to 150 AD. We wish to analyze the data to determine if there are any differences in skull sizes among the time periods. So it's actually a case of one where you may want to use the time ordering of the data, right? But surely by now, I've said it enough times, ANOVA does not assume ordering. The means for the different time periods are just means. There's no ordering in, where'd it go? These are not, it does not take into account time ordering. Now, time ordering we can do in multivariate regression, which I hope to have a little bit of time to talk about over the next 2 days. But as usual, ANOVA doesn't take into account the time ordering, which is okay, maybe. We want to see if there are any changes with time. Logical question. Researchers theorize that a change in skull size over time is evidence of interbreeding of the Egyptians with immigrant populations over the year. I don't know. Okay. To a statistician, it's just a question. How do you measure the size of a skull? Well, you ask the skull people. And the skull people say, oh, we measure these things. We must use multivariate techniques that allow multiple dependent variables. Our dependent variables are the measurements MB, BH, BL, and NH, and I used to know what those were, but I don't anymore. So there are 4 different measurements of skull size. That's probably a bone. That's, I don't know. The skull is 1 bone. I don't know. But they're measured on the same skull, right? So you have 4 measurements for each skull. So are they repeated measures? Traditionally, repeated measures are over time. So it's not like you're measuring the skull and then you're measuring the skull again and then you're measuring it a 3rd time. That's one kind of dependency. But that's not what's happening here. There are 4 different measurements of the same skull. And we're wondering, so these 4 measurements are a multivariate measurement, a 4-dimensional measurement. And we wonder if year impacts the multivariate measurements. So a mediocre analysis would be, okay, so the geologists, or I don't know, anthropologists, this is probably anthropologists. Anthropologists are mediocre at statistics in general. So you can imagine that they would submit the paper and they would look at the 4 different measurements independently, and they would do they'd actually probably do a bunch of t-tests. But if they were better statisticians, they would do one way ANOVA for each of the 4 measurements, right? Then they're going to come up with 4 different p-values. Well, and we would nail them and say, oh, you need to use MANOVA. Yeah, they need to do a multivariate analysis. So this, of course, is our old SAS notation, but I'll show you in JUMP and in other software packages, it's virtually identical. You just don't write the code. So obviously you have to tell the software that you have data. You have to tell it that you're using year as a nominal variable. The software is not going to assume that. JUMP gets it wrong, they're numbers. So it's going to say, oh, they're numerical. Then you have a weird model statement where you have 4 variables over here on the left. Typically, you've got one